Pittsburgh, today's forecast is 44 degrees with... Oh wait, I just got some breaking news in from University of Pittsburgh. Students discovered that gold and silver nanoparticles are not spherical. For some of our viewers out there, here's a brief introduction on nanoparticles.
Nanoparticles are small groups of atoms, usually metals or metalloids, stabilized by a ligand shell. Ligand is a molecule that binds metals. In the case of nanoparticles, ligands are usually small organic molecules. Nanoparticles exist at the nanoscale, which is between 1 and 100 nanometers. Due to size and surface energy interaction, nanoparticles have properties that differ from those of the bulk. The physical and chemical properties of nanoparticles can change due to variations in size, shape, and surface, as well as in composition.
Nanoparticles have many biological applications, specifically medical imaging, treatments, and gene therapy. Many biological processes, particularly on the cellular level, exist at the nanoscale. Thus, it is useful to have technologies that can be used to influence the cellular environment.
We looked at the molecular orbital energies of gold and silver nanoparticles of various sizes. We care about molecular orbital energies because oxidation relates directly to HOMO energy level, which can be functionalized for catalytic applications.
When the word nanoparticle comes to mind, many people think of spherical objects. However, under close examination, it can be seen that many nanoparticles are not in fact perfect spheres. The researchers wanted to compare the particle in a sphere energy calculations to see if it's an accurate model for nanoparticles despite their non-spherical shape. Now back to Paige, reporting live from Delaware.
Now that you have a brief understanding of nanoparticles, here's an exclusive update from the researchers' project. They will explain how their calculations were performed using a software called WebMO.
In order to accurately calculate the energies of the molecular orbitals, we had to first optimize the geometry of the nanoparticles. This was done by finding the charge and spin state with the most stable or lowest energy configuration. These and all other computational calculations were carried out using WebMO and the MOPAC semi-empirical program with a PM6 theory. A singlet spin state occurs when there are no unpaired electrons, a double when there is one, and a triple when there are two. All the nanoparticles we looked at had either doublet or singlet spin states, depending on their charge. Finding the optimal geometry of the nanoparticles consisted of testing different charges and spin states and looking for the one with the lowest total energy. Although typically thought of as neutral, we found that the nanoparticles were most stable with a charge. Once the most optimal configuration was found, molecular orbital calculations were able to be done.
We calculated the molecular orbital energy levels of the most stable spin state for gold and silver nanoparticles using the particle in a sphere model. The particle in a sphere assumes that the particle can move anywhere on the surface of a sphere. The radius of the nanoparticles was determined using WebMO. Since the nanoparticles are not spheres, two different distance measurements were used to compare to see if there were any similarities or differences. Based on the calculations, it is evident that the energy and radius had an inverse relationship. So as radius increased, the energy decreased. For example, gold 15 had a molecular orbital energy of 5.2 times 10 to the negative third electron volts, and it decreased to 2.6 times 10 to the negative 3 electron volts as the radius increased. We also calculated energy for gold 35, silver 15, and silver 35. The molecular orbital energy for silver was slightly higher than those of the gold particles. Additionally, the energy of particle in a sphere was compared to the most stable molecular orbital energy. They found HOMO, LUMO, and in some cases SOMO energies for the particles. The particle in a sphere model most closely corresponded with the LUMO energies of WebMO. Although WebMO was about 3 orders of magnitude larger than the particle in a sphere, we can see that they both show a trend in value as the radius increased or decreased. The reason behind these results could be that the calculation by hand was assuming that the nanoparticles were perfectly spherical, when in reality they were more uniquely shaped. Thus, using WebMO gives a more accurate result because it takes into account the shape of the nanoparticles.
Speaking of the shape of the extra nanoparticles, here are the pictures of gold and silver nanoparticles given by WebMO. Although they do not look exactly like the traditional orbitals, some do look like an F orbital. In addition, particle in a box wave function shown resembles several of the shape given by WebMO. However, we can see that the approximation was not good enough because the shapes did not match perfectly.
That was your exclusive update. Stay tuned in for the 9 o'clock news where Anderson Cooper interviews Maddox Jolie Pitt about the Bradulina breakup. Thanks for watching!